So we're going to go ahead without Eric, and I'm going to go ahead and introduce the 4 speakers, and we'll let Paul get us started here. So we have 4 speakers in our session 2 this afternoon: the ocean-land-atmosphere interactions of the Continental Americas and the Caribbean. First speaker up is going to be Paul Durmeyer from George Mason University. He's going to be speaking on the water cycle linkages between the Intra-American seas and Continental Americas. Following Paul is Isabel Hoyos. She's from the University de Antigua. She's going to be speaking on the moisture origin and transport processes in Colombia and northern South America. Following Isabel is Julian Ruano. He's going to be speaking on the question, do the Amazon and Orinoco freshwater plumes really matter for hurricane-induced ocean surface cooling? And then our last speaker for session 2 this afternoon will be Lakshmi Krishnamurthy. She's from UCAR GSDL, and she's going to be speaking on the seasonality of the Great Plains, low-level jet, and INSO relationship. So with that, let's take Paul off mute if he isn't already. And Paul, can we go ahead and test your audio?
Okay. How do you hear me?
We hear you great. Go ahead, and you are in control.
I'm in control. Oh, boy. All right. Well, thank you for this opportunity. This has been quite interesting. I think this is the first conference I've ever attended barefoot, so this is nice. I'm going to speak today with something of a change of gears from our previous talks, looking at the water cycle linkages between Intra-Americas seas and the surrounding continental areas. And first, I need to spend a little bit explaining the methodology. This is something we've been doing for quite a while, calling it the Quasi-Isotropic back trajectory approach. Essentially what we're doing is we're treating water vapor as a passive tracer to try to understand what's the point of origin for water that falls as rain at any particular location. And we've borrowed the idea from air pollution meteorology with this idea that at least between the point where you have evaporation and the point where you have condensation and rainfall or precipitation, water vapor is essentially a passive tracer going along for the ride. And so the key technique then is really what do we do about those endpoints where we have to make some assumptions. And so we trace backwards in time with this method. We start where there's a precipitation event in space and time, and we use wind fields, temperature, humidity information, principally from reanalyses, to understand the circulation and the atmospheric states. Generally, we use observed precipitation data sets for determining the rainfall events, and we are also using the reanalysis estimates of evaporation along the way to try to understand where the moisture originated. So each trace generates essentially a probability density function, or a blob, as we say, of the evaporative sources that supplied rainfall to a particular location or region over some period of time. And this can be aggregated in many ways in space or time. Our sort of fundamental window for calculations is 5-day periods, pentads, but we can sum those up to look at months or seasons or years. And so this is kind of a cartoon of what it looks like. Essentially, we launch parcels, these Lagrangian elements of rainfall, each one corresponding to a certain amount of rainfall. Typically, we divide up rainfall over a period of time into equal amounts and have a tracer for each, which will be anywhere, usually on the order of 100 per grid box per pentad, if there's any rain in that time. And so we trace them backwards. First we launch them randomly in the vertical, weighted by humidity, the assumption being that every water molecule in the column in the troposphere has an equal chance of getting condensed and rained out. So we start with that kind of profile, which means most of our starting parcels are going to be very low in the atmosphere, where most of the humidity is. Occasionally you get one in the middle or upper troposphere. And then we trace them backwards on isotropic surfaces using the wind information, stepping backwards. And in so doing, every essentially model time step along the way, we look at the evaporation amount below the parcel and the total precipitable water in the column, and the ratio of the total evaporated water in the time step to the precipitable water in the column is our estimate of what fraction of the water came from evaporation in that point. So we're not treating the parcels as discrete. We're actually shaving them off as we go backwards in time based on the rainfall rate. And we typically trace back either 15 days or until we've accounted for at least 90% of our original water, and then we do a little bit of scaling to make sure that our budget's closed. Give you an idea of what that ends up looking like. This is a, oops, hit the target, there we go. Here's an example of the evaporative source that would be supplying rainfall, in this case over this box, the upper Mississippi Basin, during the summer of 1993, which was a flood event, particularly in June and July of that year in that region. And I'm sorry, this doesn't have the scale on it, but essentially I think each color is a factor of 2. So essentially most of the evaporation tends to be nearby, either over land or ocean, depending on the location. And what you can see is the signature of the prevailing winds in this case. In this particular work, which was the first that we did back in the late 90s, early 2000s, looking at the particular case of the 1993 floods and the 88 droughts, we found that there seemed to be an anomalous, large amount source of moisture coming from the western Gulf of Mexico into the Caribbean Sea, supplying moisture all the way into the northern United States. And since then, we've redone this a couple of times. Initially, this work was done with the NCAR reanalysis data. Later with the R2, NCEP DOE, and most recently with MIRA, we've done this. So I'll show you some examples as we go along, and then focus in on the Intra-Americas Seas region. So this 93 flood in particular was very outstanding in that you can see precipitation anomaly is on the x-axis in millimeters per day over the Midwestern United States. And the y-axis is the source of moisture from the Caribbean as we've calculated it, or the anomaly in that. And there is something of a positive correlation in time that goes through there. I'll show this in a different way later. And then the 1993 case was an extreme outlier in both precipitation anomaly and this Caribbean source. This was work that we had done looking at data through 2004. In 2008, another major flood came along in the Midwestern U.S., and that prompted us to go back and look at that case and compare it to 93. And what we tried to dub, it didn't really take, but we tried to dub this the Maya Express, kind of the counterpart of the Pineapple Express you hear about, with the large atmospheric rivers, essentially, the moisture sources coming from the subtropical Pacific, feeding moisture into the west coast of the United States, California, Oregon, Washington, even up into British Columbia. So what we find is that there's occasionally a similar sort of feature where you're sort of linking the characteristic Great Plains low-level jet all the way back to the Gulf of Mexico and into the Caribbean and the tropics in the Intra-Americas Seas region. This seems to be linked with extreme flood and precipitation events in that location. So we had a paper in EOS about that. And essentially here we show at the top, these were the precipitation anomalies for June and July 1993. And on the right is May and June, a little earlier in the year 2008. So the blue shaded regions were the core of the flood in those cases. I hope you can read the scale. This is in millimeters for the 2-month season, going 2550 all the way out to 250 for the most purple shades. And then below is the anomalies in the evaporative moisture source supplying rainfall in each case. And in both cases, you see that sort of near-field continental sources are showing as brown. In other words, less evaporation from over land nearby than you would typically see climatologically during these seasons. And the blue areas sort of trace out where we're seeing more evaporation supplying it. So you can kind of see this atmospheric river from the Caribbean tracing up across sort of Texas into the southern Great Plains that was feeding rain in 93. And a similar feature in 2008, it's a bit broader, shifted a bit further to the east, but supplying again sort of from this Inter-Americas Seas region. Very far afield from the place where the rainfall anomalies were happening. And this panel is just showing that there was actually anomalously high precipitation in the months before the floods in each case. And there has been some speculation about local soil moisture feedbacks that may sort of exacerbate the local flooding. But it's not all just a general circulation occurrence, but there could be local feedbacks as well. Now, the U.S. Great Plains in particular is interesting because it shows up in many different calculations as this hotspot of land-atmosphere interactions, I say. It's also a hotspot for precipitation variability. So in this case, what's shown in shading is the variability in rainfall when we look at 5-day averages of rainfall as our sort of base unit, look at monthly precipitation totals and seasonal precipitation totals. In each case, you have this band from the Gulf Coast up through the Great Plains that has higher variability in rainfall than any points to the west or to the east or to the north. And as you go to the longer time scales, the center of action shifts from the Gulf Coast to being spread much more into the central U.S. So this is a region that has a lot of variability and interest, and being a major agricultural region, not necessarily a place you want there to be a lot of variability and uncertainty in the rainfall. So going back to these moisture sources again, this is now a more general climatology for basically, again, this area, this box outlining a region of the Great Plains, May, June, and July. This is the mean evaporative moisture source that supplies rainfall over this box. So you can see it's kind of centered, shifted slightly to the west of that box. You kind of see a leg that extends down, tapping into the Caribbean. There's also, by these calculations, which was using the Sept DOE reanalysis, a lot of source from the Pacific. It might be anomalously high just because of the low resolution of the reanalysis. We think there's probably more moisture transport over the Rockies in the reanalysis than what we really see in reality, but we do seem to have some there. And in the wettest 10% of all months during May, June, and July, we see this tendency for moisture to be tapped much more strongly from the Gulf and from the Caribbean, and much less from the local fields. In the driest years, interestingly enough, the local recycling, which means the coloring over the box, is also brown, also very low, but so is the remote sources, and what moisture does come tends to be from the continental regions to mostly to the south. So it's interesting that the time when you have the greatest recycling or local source of moisture is not the extreme dry or the extreme wet, but when things are kind of in the middle. Looking at that Caribbean source more particularly, this is the correlation between the May, June, July rainfall in that Midwest box and just general sources of Caribbean moisture supplying all these different grid boxes in North America. It tends to be very high not only into that flood region, but also in the southeast and eastern U.S. All of these areas tend to be receiving a lot more Caribbean moisture when there is flooding occurring in this area, in this case sort of the northern, northeastern Great Plains. And here you can kind of see our definitions for Gulf of Mexico, Caribbean. And I'll also talk a little bit later about this sort of tropical or Pacific, Northeast Pacific source as well. Now, most recently, we've repeated this calculation, higher spatial resolution using the MIRA, NASA MIRA reanalyses. Again, we use the temperature, humidity, wind fields for the positioning of the isotropic layers and doing the advection. Precip, we use the MIRA data corrected by the CPC Unified Precipitation to try to remove the biases and errors. So basically, scales of pentat and larger at CPC data, and the smaller timescale variability, we're just superposing the MIRA variability on that. ET is from a MIRA land offline product, which corrects some of the problems in the MIRA reanalysis. And so when we do that, well, you can do a lot of things actually with this data, not just linking sources and sinks. We can do an overall assay. Here I'm just showing for fun kind of the global estimate of terrestrial or continental sources of moisture supplying rain at each point. And so you can see, Central Asia, most of the water that falls as rain is evaporated from land, not from ocean. That's what this is saying, more than 90%. You see the Americas tend to have a much higher fraction of water falling that's being evaporated from over oceans, which means the blue colors, low fractions from over land. But what you do see in sort of Intra-Americas seas region, particularly northern parts of South America, north of the equator, are areas which we find have some of the largest fractions of terrestrially evaporated moisture falling as rain. And that's largely because of the winds in this area. You're in the trade winds. It's an easterly wind. You're getting moisture that's evaporated from points upstream, or in the case of the Guyana region, moisture from the Amazon, which often trails up into this area and then falls as rain. So it's kind of an interesting contrast between east and west. Okay, so actually let me skip over that and get to the regions here. Sources and floods. This is now showing kind of a more general climatology of the region. March, April, May. This is the fraction of total rainfall in a particular region that's contributed by evaporation from the Caribbean Sea. So the brightest purple areas, 30% or more of the rainfall is from those areas. And you can see how it decreases radially outward. But a lot more of that moisture is heading north in the circulation than is heading south into South America. This is the change in that percentage, the deviation from that in the wettest 10% a month. So central Mexico, for instance, gets more rain from the Caribbean when they're having floods. Likewise, we see that kind of in the Great Plains in Louisiana. Not in Texas. Texas, when they're having floods, the rain is less coming from the Caribbean, and actually I'll show more of it is coming from the Gulf of Mexico. So if we kind of move along here, this is June, July, August. Again, something similar. Here we do see that dipole here. It's interesting, the northern regions get more of their rain from the Caribbean when they have floods, but the southern U.S. is getting less from the Caribbean. And as we see in the next slide, more of it from typically the Gulf of Mexico. I'm actually showing DJF now, the wintertime signal, just because it's a little bit more interesting. But we see this almost year-round. Texas and a lot of areas in the south get their flooding moisture more from the Gulf of Mexico than the Caribbean. So it's weird. You kind of have this leapfrogging effect in terms of near and far sources into the U.S. And here's the Northeast Pacific source. It's basically anything along this coastline tends to come in this case for JJA, supplying a lot of the monsoon rains in Mexico. The changes, though, in JJA are actually pretty mild. There's not a lot that's going on in terms of supplying anomalous rainfall, suggesting when you do have floods in these regions, it's not that you're having extra moisture being brought in from a particular location. It's something local, some sort of stability and atmosphere feedback, something that's not tied to the circulation is the suggestion. Here's the Northeast Pacific source now, September, October, November, when we get into the sort of the tail end of the North American monsoon. Now suddenly we see signals in north central Mexico into the southwestern U.S. where above average rainfall does tend to be associated with more moisture being brought in from the Pacific Ocean. Interesting, over sort of the Four Corners region, there seems to be less moisture when they have heavy rains in September, October, November. And I did mention the bottom one. Instead of a percentage, the change in the percentages, the bottom is the actual change in mass of water that's being delivered. So a little different way to quantify that. So just to summarize, back trajectories of water vapor from the precipitation sinks backwards in time to their evaporation sources kind of give us a new perspective of the atmospheric water cycle and how these distant locations can be connected through the atmosphere. And we can quantitatively compare the variations in source regions during these dry, I didn't show dry, I mostly showed wet periods to elucidate linkages and even causes or lack of causes when we don't see a connection to remote moisture sources with extremes. That suggests something else is happening, like a local feedback. And I'll stop there. Thank you very much.
Great. Thank you, Paul. We're going to see if Eric Rivera, you should be off mute, and he's the chair of the session. Are you able to join us?
Hi. Yeah, can you hear me now?
Yeah, you're a little faint, so please speak up, but we can hear you.
Okay, well, thank you very much. I really apologize for the audio problems I had. I don't know what happened. But anyway, I think this is a very interesting talk. I just have a question for Paul. Paul, do you have any chance to look at the relationship between extreme precipitation in the western United States during the cool season or during the winter, moisture originated from the Caribbean Sea or the tropical Eastern Pacific?
Yes. What we find is that Caribbean moisture source, whether it's climatological or anomalous, really seems to stay east of the Rocky Mountains in North America. It doesn't really seem to penetrate into the far western U.S. But on the other hand, the Pacific source does tend to be connected quite a bit with anomalous precipitation outside of summertime, outside of JJA. In other seasons, we do see connections there. Sometimes it seems to be connected with hurricanes, landfalling Pacific hurricanes that make their way north across the Sierra Madres in northern Mexico. And other times it seems to be more like the atmospheric river phenomenon.
Okay. Thanks.
Great, thanks. We have two more questions, and then we'll go on to our next speaker. We have a question from Eric Alfaro. What is the relationship of the result in slides 13, 14, and 15 with the CLLJ? I apologize, I don't know what that acronym is.
Yeah, the Caribbean low-level jet. Yes. Okay. So these regions, as you can see, we don't tend to get shading in Colombia or any place in sort of northern South America. In these cases here, we get a little bit in Panama, but we don't, at least in this data set in our calculation, we don't see a connection with rainfall anomalies in this region and changes in the moisture transport. So that kind of suggests that maybe it's changes instead in maybe low-level convergence or something that's not the advective term, but maybe something dynamical or something to do with stability in the atmosphere. So it's kind of by process of elimination, at least, where it seems like we're not having a connection with the Caribbean low-level jet transport and rainfall anomalies, at least on monthly timescales. Perhaps if we look at higher time resolution, we might see something different.
Great, thanks. We'll do one more question, and we'll queue up the others for you to respond offline. But Eric Munoz had a question. Jill, can you take him off mute, please? And Eric, you can, or Ernesto, excuse me. And Ernesto, you can just ask your question.
Go
ahead, Ernesto.
Ernesto, go ahead. Okay, I don't hear him, but I think he typed something in, so maybe I'll just ask it for him. He said, can you show the slide of the MAM Great Plains sources?
Okay, let me see. Well, this is Caribbean sources for MAM. I'm not sure if this is the one or if it's further back.
Okay, he wants to know, is there a possibility that the Caribbean is not a source of moisture, but that the winds are still part of the greater pattern?
Oh, sure. Well, first of all, there is some blue shading here. It's in this particular data set, it came out weaker than when we've used in-situ analyses. Certainly, circulation features can have something to do with that. And like I say, large-scale lifting or subsidence, the larger dynamical situation can certainly affect the rainfall anomalies, even if the moisture advection does not seem to be changing. And that's why I say when we see no connection, we can eliminate one thing off of our list of causes for an extreme, but that still leaves the others to be investigated.
Okay, thank you. Can you hear me now?
Yes. Is this the right slide?
Sorry, I had it on mute, but thank you for your answer.
Okay.
Great. Thanks, Paul, and thanks, everyone. We're going to go on to our next speaker. If we didn't get to your question, we'll queue that up for Paul, and he can respond after the workshop, and we'll make sure you see that. So thank you, Paul. We're going to go ahead and get started. Yep, with Isabel.
Okay. There's a lot of extra slides here, too, to skip over. I don't know.
Great.
One more. There it is.
One more. Perfect.
Thank you.
Yeah, thank you. Isabel, are you there? Can we test your audio?
Yes, I can hear you. You can hear me?
We can hear you.
Hello. Okay.
Go ahead and get started. Thank you.
Okay. Good afternoon. I'm very glad to be here and share some of my PhD results. This work has been developed as part of my doctoral research with the advice of Continental and Julio Cañón. We address the problem in a twofold way. We review the spatiotemporal variability of regional precipitation and moisture fluxes, and we study the sources of regional moisture and their seasonal variability. Colombia is the northernmost South American country, characterized by a very heterogeneous landform because the Andes are split in 3 branches, and as a result we have 4 large basins. The Caribbean Basin with the Magdalena River that contributes with 3% of fresh water into the Caribbean Sea. We have the Pacific Basin with a large tropical rainfall and large values of annual rainfall. We have also the Colombian portion of the Amazon River Basin that is almost completely indigenous territory with large protected areas. And finally, we have the Colombian portion of the Orinoco River Basin with low grass crops and large floodplain areas. This is a very sensitive area because it is experiencing important changes in land use. As a tropical country, the seasonality in Colombia is mostly defined by the annual cycle of precipitation. The spatial variability of regional rainfall patterns is the result of annual migration of ITC Sept and its interaction with the regional orography. Here we have the annual cycle of precipitation in each one of the Colombian basins in left side, and the regional moisture flux divergence. Here, the colors represent convergence and the red ones represent divergence. As expected in tropical areas with a low level convergence and high surface temperature, the moisture convergence follows the rainfall patterns. Precipitation in the Caribbean Basin shows a bimodal annual cycle, highly sensitive to the IASCLiP state. We have moisture divergence during the dry season here, and moisture convergence during rainy seasons here. Precipitation in the Pacific Basin exhibits the most complex pattern with large annual values of precipitation, and here we have a permanent convergence zone because of the confluence of moisture from the North Atlantic and the Pacific Ocean and the blocking effect of the western flank of the Andes. Vertically integrated moisture transfer from the Pacific Ocean only plays an important role during the second rainy season here, as you can see. Okay. The Amazon and Orinoco Basin have a renewable cycle of precipitation with maximum in May and June respectively. In these areas, the moisture convergence is sustained by evaporative source, and the ITCC moves slower than the rest of the terrain. The dry season occurs when the ITC set is at its southernmost location at the regional orography deflects the easterly moisture flux southward. Qualitatively, regional patterns of precipitation are well represented by area interim and twin data sources. However, area interim overestimates the precipitation amount in the Caribbean and the Pacific Basin and underestimates the precipitation amount over the Amazon and Orinoco Basin. This gives us a general description of the regional moisture transfer processes, but we can't know the specific origin of affected moisture. So, to understand where the regional moisture comes from, we have used 3 complementary approaches for different backward trajectory models. The simplest model is a semi-Lagrangian model that calculates water vapor and precipitation contribution from self and source regions. The back trajectories are followed until they exceed the domain, but most of the real contributions are collected in the last few days, usually no more than 10. In the Quasi isotropic backward trajectories, of course, was about a couple of minutes before the precipitation event. In a 5 days temporary window triggered the backward moisture tracking. The initial position of tracked parcels are randomly fixed, and the elevation is defined probabilistic weighted by the vertical distribution of moisture. Each parcel is tracked backward no more than 15 days, and it provides the evaporative source supplying precipitation in the target region. On FlexPart, the most complex model is based on a dispersion model that fills the atmosphere with a large number of computational particles that adopt the properties of physical systems. So the position of each particle at a later time is determined by the dynamical evolution. The trajectory of each particle located in the target region is followed backward 10 days. FlexPart accounts for the net loss or gain of moisture along backward trajectories that evaporation and precipitation cannot be disaggregated. Our target region includes the Caribbean and the Pacific Colombian Basin, and it is exactly the same for FlexPart and for DRM, that CIBT uses the slightly smaller Magdalena Basin as the target region. We refer to this region as NOSA. So in FlexPart and DRM use input data from ERA interim, and CIBT uses input for MSEP. As you can see here, there are some agreements and differences between the three models. Among the three models in this climatological map, you can see contributions from the tropical Atlantic are present in all of the three models. DRM and FlexPart capture contribution as far as the tropical North Atlantic, while CIBT shows oceanic contributions concentrated in the tropical Atlantic, even reaching the Western Africa. In CIBT, the moisture from the Pacific Ocean is limited to the adjacent Pacific, while the FlexPart exceeds longer range contribution over the tropical South Pacific. You have to be aware that there are some differences in the scale of each one of these models, and we have to here we can see also that the research sources have important contributions in all of the three models. And I would like to highlight that in FlexPart, net gain of moisture along the trajectory is represented by positive values, and net loss is represented by negative values. Okay, based on this climatological description, we have selected the regions that potentially contribute to our target regions. These are colored in the map, and we can see that the terrestrial source corresponds to the main hydrological units here, Orinoco and Amazon Basin, and the oceanic regions have been delimited in agreement with the sources generated by FlexPart in the Pacific Ocean and Atlantic Ocean. As you can see here, more than 80% of total contributions come from Atlantic Ocean, terrestrial source, and the adjacent tropical Pacific. The biggest contribution comes from tropical Atlantic, followed by terrestrial sources. We would like to highlight the importance of Orinoco, the local recycling also, and the Amazon and the Amazon basin. Now we will discuss the seasonal variability of the most important sources in the three models. After summer, when the ITC set is at its lowest position, the main monster contribution to North comes from tropical North Atlantic, in agreement with the RM and FlexBar. As a qualitative same result can be found in QIBC, but with a smaller contribution, as you can see here. The three models also show an important contribution from the Caribbean Sea that is notable during Australian spring and summer. Also, FlexBar shows a significant higher contribution than the and QIBC, as you can see in the picture. As ITC said, more notable during the austral fall, the contribution from tropical North Atlantic diminishes, and in contrast, moisture inflow from tropical South Atlantic increases and reaches its maximum in August. Please again be aware there are differences in the scale of contribution, and we have a very similar behavior in our model, but some important difference in the magnitude of each model. So, the recent moisture sources are best understood by considering the DRN and the QIBC. The reason is that in FlexBar, as the parcels move into the terrestrial tropical regions, the trajectory is calculated. We have negative values of evaporation minus precipitation during time period because precipitation is larger than evapotranspiration. However, even if evaporation is more than precipitation, the evapotranspired moisture can include transfer to other regions and serve as precipitation to the DRN and QIBC can provide some information about these terrestrial sources. You can see that the recycling has the binary cycle, and in FlexBar we have a predominance of precipitation here during the rainy season. The adjacent Pacific Ocean contributes significantly to the mean total precipitation water during October, November, and December. The South Pacific has a considerable higher contribution to tropical North Pacific. With growing long-range transport into this region, this feature is related to the streaming excuse me. This feature is related to the streaming of the westerly flow at ground levels that is now at Southward. Such increase in the convergence of moisture is associated with a peak of precipitation, as we can see here, FlexBar with a prevalence of precipitation for FlexBar in the tropical North Pacific, and a good agreement between FlexBar and the RM during the Southward season. Okay, in summary, in the first dry season, I'm right now. In the first dry season, with the ITC set in its lowest position, we have significant contribution moisture from North Tropical Atlantic and small contribution from the Pacific Ocean because this is the end of the Southward season. Local recycling and Orinoco contributions are also present. The first rainy season with the ITC is in transition from the lowest position to higher position, and it's co-located over this area. We have minor contributions from North Tropical and Tropical Atlantic, but not contributions from the Pacific Ocean. We can also see the beginning of a contribution from Amazon Basin and significant local recycling and Orinoco contribution. When the IPC sets in its northernmost position, we have important contributions from the tropical South Atlantic and tropical Atlantic. And also recycling at terrestrial sources are important. And finally, during the second rainy season, when the IPC set is moving toward its lower position, we have active contributions from Pacific, Atlantic, and of course we have also terrestrial source as important contribution. Okay, finally, the annual cycle of precipitation in each Colombian basin is driven by the interaction of the IPC set with topographic, and it is reflected in the spatial patterns of moisture flux convergence. Three different methodologies to evaluate atmospheric moisture sources indicate that marine sources are the most important contribution for Colombia. And of course, we have highlighted the importance of terrestrial sources in our country, and this could be potential have implications related to changes in vegetation and land cover uses. Okay, I think it's all. Kristen?
Great. Thank you, Isabel. We have time for one question. I'll ask you the question that came in from Eric Alcero. He asked, any idea on the occurrence of the MSD in Pacific and Caribbean slopes during the same month of July? And he means in the observation curve.
I suppose we have some contributions from Caribbean low-level jet here, as we can see in our cartoon. Let me find it here. We suppose that this is a seasonal effect of Caribbean low-level jet, but we are not sure because it's not. We don't have a strong evidence of that processes.
Okay, great. Thank you. We're going on to our last speaker. Thank you very much, Isabel. Julian, you're going to be up, and I think Jill has unmuted your audio.
Yes.
All right. Julian, can we try you again?
Yes, you listen to me?
Yes, we can hear you. Wonderful.
Hello.
Thank you.
Okay. So I'm Julien Joanneau from IRD in Toulouse, and I'm working in Lagos. The question we would like to answer is, do the Amazon and Orinoco freshwater plumes really matter for hurricane-induced ocean surface cooling? And this work has been mainly done by Olga Mendez, a postdoctoral researcher at Tele. So as you can see on this satellite data, is that Amazon and Orinoco runoff influence the large-scale salinity and temperature distribution. We see here the Amazon plume, the Orinoco plume, and linked with these low salinity values at the surface, we have warm temperature. And so the mechanism often proposed to explain the link between low saline values and warm temperature is twofold. First, the density difference between the plume and the subsurface water may limit the vertical mixing, and so will maintain the warm water at the surface. And second, the high concentrations of phytoplankton, dissolved organic matter, sediments, capture the incoming solar radiation in the first method, and so on, favor the warming of the upper ocean. So one key point is that the tropical cyclones often pass directly over the Amazon-Orinoco plume, as illustrated here by the main path of the tropical storms and weekends given by field, which we see here in color, and we see that they are coincident with part of the Amazon river plume in red. And field observed that 68% of all Category 5 Atlantic hurricanes during the 60-2000 time period passed directly over the historical region of the plume. So the question she asked is, do Amazon and Orinoco plumes are active players of TC intensification in the region. So two causal relationships between the river plume and tropical cyclogenesis are generally proposed. The first is that the presence of particularly warm SSTs over river plumes could favor their development. And this has been verified by Lizzie and Cook, who show a good sensitivity of summertime climate and recurrent intensity and frequency to temperature anomalies over the Amazon Orinoco plume region. And the second point is that and it will be the main focus of our study, is that the inhibition of TC-induced surface cooling by the presence of low saline waters at the surface, and also the presence of barrier layers, could favor TC intensification by weakening the cool wake and its impact on the hurricane growth potential. So next. This last hypothesis has been strengthened in the recent years by observation. So first, observation of the Hurricane Katia, who traveled in 2011 across the river plume. And we see that the cooling within the plume is weaker than outside. And from an ensemble of storm tracks, Roll et al. In 2014 have shown that cooling is systematically reduced by 50% in the plume waters compared to surrounding water, with cooling about 1.5 degrees in open ocean waters. So here there is a mistake in the legend, to the contrary. So 1.5 in open waters and 0.7 in plume water for all the category of hurricanes. So the objectives of this study are first to clarify and quantify the impact of the Amazon and Orinoco freshwater flux on the TC response, to detail the processes setting the characteristics of the sea surface cooling induced by tropical cyclones, specifically in the region of the Amazon Orinoco, and three, to explain the difference of cooling between the plume region and the open ocean region. So for that purpose, we set up a regional ocean model. Here is the domain. The model is a NEMO at 1/4 degree. It's an oceanic model with 75 vertical levels. We force at the surface using ERA interim data and the large and Jaeger bulk formula. And the analysis period is 1998-2012. And two experiments are carried out. First, a reference with river prescribed from Diane Trenberg climatology, and another experiment without runoff. And we use different observations from hybrid tracks, TMI and MSRE SST, ISAS, which is the narrow-based climatology of TNS, and mixed layer depth and barrier layer thickness are also from Argo. We have a specific hurricane forcing strategy. So hurricane winds are fully represented in reanalysis products such as CORE2 or RI. And moreover, the linear interpolation of the forcing at each time step erodes the fast-moving wind pattern. So our strategy follows the method described in Vincent et al. 2012. So the hurricane position and intensity are from ID tracks and are 6 hour and 10 minutes sustained wind product. We filter out residual TC signature in the ERA interim forcing within 11-day running here within around each vortex. So this is allowed to remove the residual TC signature. And then at each model time step, we add a TC wind pattern to this field. And this ensures that both temporal and spatial evolution of the TC are captured in the model. So the TC wind pattern computed using a Will-Have-By and Tele ideal vortex and depend on the IB track's maximum wind. Moreover, we modified the drag coefficient for wind speed higher than 33 meters per second in order to mimic the observation by Paul et al., which show a drop-off of the drag coefficient at very high wind speed. So first, let's see the background condition in the model compared to observations. So in terms of SST, we have a bias weaker than 1 degree Celsius. we are able to reproduce the Amazon Orinoco plume in agreement with observations. The mixed layer depth in a plume region is about 10 meters, in agreement again with observations. And we have a barrier layer thickness of about 20-30 meters, again in agreement with observation. So now let's see what occurs when we compare the experiment with runoff and without runoff. So without runoff, we increase the sea surface salinity, obviously. We reduce the barrier layer thickness. We avoid it almost. We increase the mixed layer depth by about 10-20 meters. And we have a very weak impact on the sea surface temperature and almost no significance in the plume area. And this, the net flux is almost unchanged. So now let's see the difference of cooling in the cyclone wake. Here I show the time evolution of the temperature in the plume area when a tropical storm or hurricane pass at time 0. So we note a cooling of about 0.3 degrees, which its maximum value 2 days after the storm passage. We see that the model and observation are in good agreement, observation in green. This is for the plume area, and when we are in the open ocean area, we have a cooling which is much stronger and of about 0.7 in average. Now, if we look at this cooling at 2 days after the storm passage for different storm categories, so tropical storm, tropical depression, category 1 and 2, and category 3, what we see is that for river plume, the cooling within the river plume area is always much weaker than open ocean water. Moreover, if you compare the black curve with the red curve, this shows that without runoff in red, we only increase the cool weight by 10%. So this suggests that self-stratification cannot explain the 50% cooling difference we have between the plume and the open ocean water. So in order to see what processes control the cooling in the wake of the cyclone, we perform a mixed layer heat balance. So the local tendency of temperature, the advection contribution, and the RC fluxes and the vertical mixing are the main contributor to this balance. And what we can see here is that for the plume waters, for tropical storm, tropical depression, and up to category 1 and 2 hurricanes, the RC fluxes are the main contributors to the surface cooling. And then for the stronger hurricanes, vertical mixing in red contribute mostly to the cooling. In open ocean waters, we see that vertical mixing take a greater part even for category 1 and 2 or tropical depression. So one question is why the surface cooling contribution of vertical mixing is weaker in the plume region and in both experiments, with or without storm. So 2 metrics were found to be useful to explain this. First is the cooling inhibition index, which is an index which gives a proxy for the amount of energy required to cool the ocean surface by 1 degree by vertical mixing only. And another metric which is helpful is the depth at which ocean temperature is 2 degrees below the sea surface temperature. So let's see. Here I show the depth at which SST minus is equal to the depth at which temperature is equal to SST minus 2 in observations. What we see is that in the plume area we have a relatively deep heat content, and we also see that the cooling inhibition index is quite high. This means that a lot of energy is required at least more energy is required to cool the surface than in other regions more north. In the REF experiment, we are able to reproduce the main patterns of SST-2 and cooling inhibition index. And what we see is that when we remove the runoff, we have almost no change of the thermal content here, but we reduce the cooling inhibition index by about 20%. But this value remains still quite large. One interesting point is that we have a larger thermal content in the plume area compared to region more north. So one question is why the surface cooling contribution of vertical mixing is weaker, still weaker the image. Sorry. And so what would if it's not the river plume which controls the large content in the plume area, what could it be? And what we can see is that the content as seen here using the depth of the term 23 degree is well explained by a linear Rossby wave model by the weak Driscoll. So suggesting that the first order driver of this deep content is not in the plume area is not the salinity stratification, but the large scale wind field. So in conclusion, the model results suggest that the effect of runoff and barrier layer on the tropical cyclone-induced SST cooling only lead to a 10% weakening of the cooling. And instead, we found that the temperature stratification driven by the large-scale wind plays the main role in explaining the 50% observed difference of cooling between the plume and open ocean water. So these results are currently under review for GGR, and our ongoing work is to develop a fully coupled regional model based on NEMO and WRF to test the sensitivity of cyclogenesis to river runoff and ocean color also. Thanks very much.
Great. Thank you very much, Julian. Eric, do you have any questions before we turn to the audience?
Yeah, I just have a short question. Have you noticed like any special trend in the river discharge, like a historical trend in the river discharge from the Orinoco and Amazon rivers?
I'm not sure to have well understood the question.
Have you noticed, or do you know of any changes in the river, the discharge from the Orinoco and Amazon rivers that could eventually affect the reduction of the cooling on the Atlantic Ocean?
Well, we are taking into account the seasonal cycle. This is the point.
Excuse me? My question is that is there any in your model, or would you eventually consider any changes in the discharge from the Orinoco and Amazon rivers induced probably by human activity?
Yes. No, I'm not sure. I'm not sure to understand. I'm sorry.
Okay, I can send you the question.
Write it.
Type it. Yeah, I will type it. Okay.
That would be great.
Sorry.
Thanks, Eric. We do have another question from Ernesto. Ernesto, you should be off mute. Joe will take you off mute, and you can ask Julian your question.
Okay. So the question is whether there is a trend in the discharge of the Amazon and Orinoco. I'm specifying.
Yeah. Can you hear me?
Yeah.
Can you hear me, Julian? Okay. Hi, this is Ernesto. So basically, I think I'm wondering whether Eric was trying to ask that question that I wrote, but probably he referred also to variability. Basically, I think he was asking whether the model, your simulations are capturing the variability and perhaps the trend. And so one question is there a trend in the discharge in any of these two rivers, and how does your model deal with that?
There is no trend. We are specifying a seasonal climatology of river runoff. And regarding the very strong sensitivity test we are doing, we completely remove the runoff, and we see almost no impact on the background temperature and on the cyclone response. So I guess that a trend will have not a strong effect, at least in our forced simulation. Probably in a coupled simulation, it may the sensitivity may express more stronger.
Thank you.
Thanks, Julie. And did you see the comment from Julio Scheenbaum? He wrote that in yours in the Scheenbaum 2013 paper, we say that entrainment may be important if there is a barrier layer. Why do you think it is not important in your results?
Effectively, what I presented, the mid-layer balance I presented is not really a mid-layer balance. It's a balance over the first upper 2,200 meters. So I didn't look at the entrainment value, and yes, this is my point. So I cannot answer Julio.
Okay, great, thanks. So I think we're going to have to move on to the final speaker to be aware of time. Thank you very much, Julian, for your presentation. If anyone has any additional questions for Julian, please go ahead and type those in a chat to us. We're going to pull those out, and we'll make sure he receives them and responds to everyone. Okay, and Lakshmi, you are up. Can we test your audio?
Yeah, can you hear me?
We can hear you fine. Go ahead.
Thank you for giving me this opportunity to present my results. Today I will be talking about the seasonality of the Great Plains low-level jet and ENSO relationship. I would like to acknowledge the contribution of my co-authors towards this research work. Before I present my results, I would like to give a brief overview about what is Great Plains low-level jet and why is it important to understand the Great Plains low-level jet variability. The Great Plains low-level jet manifests itself as the maximum in the meridional winds at 925 hectopascal. And when I refer to the Great Plains low-level jet index, it's the area average winds in this blue box. And this is a very important climatic feature of the Intra-Americas seas. It transports the moisture from the tropical Atlantic over to the United States with the help of a Caribbean low-level jet. Caribbean low-level jet is the maximum in the zonal wind at 925 hectopascal, and the index is referred to as an area average zonal winds in the green box. So why do we need to care about Great Plains low-level jet? As I mentioned in the previous slide, it serves as an important source of moisture to the continental United States. And also it has a profound influence on the regional hydroclimate, tornadoes by changing the vertical wind shear and the moisture availability, on agriculture and forestry by affecting the seed dispersion and the rainfall variability. It also does affect human health through the seasonal migration of birds, which in turn assess the influx of pests and disease-causing agents. So this suggests that it's important to understand the factors which control the variations of the Great Plains low-level jet, as this can have profound socio-economic implications over the United States. The motivation for this work arises from this result. Here, point correlation of meridional winds at 925 hectopascal with the Great Plains low-level jet index, which I described in the first slide, is shown. In the bottom panel is this similar correlations but with SST. The left side is for the spring season and the right side is for the summer season. As you can notice here that the strong Great Plains low-level jet is associated with a La Nina phase during spring, whereas in summer, the stronger Great Plains low-level jet is associated with an El Nino phase. So it suggests a seasonal change in the relationship of the Great Plains low-level jet with the tropical Pacific SSTs. So this seasonality in this relationship is quite intriguing. The first thought was that probably this is just occurring by random chance because of the limited sample size in the observation. But the review of literature suggests that the published studies has an apparent split into two categories. One group of studies which suggest a negative correlation where La Nina is associated with a stronger Caribbean low-level jet is during the spring season, and there are another group of studies which suggest a positive correlation where an El Nino is associated with a stronger jet. So because of this peculiar relationship, we have three objectives for this work. One is to test whether it is a statistical artifact coming from a finite sample size, or is it a true seasonal change in relationship. Suppose this relationship is not spurious, we wanted to test if current coupled climate models can capture the seasonal change in this teleconnection. And the third objective was to understand the mechanism through which this seasonal change in teleconnection can happen. So the approach we employed is, because of the limited sample size from the observations, we test the robustness of the seasonality in a long control simulation from FLORE. FLORE is one of the GFTL's coupled climate models, which has a high resolution in atmosphere and a low resolution in ocean. Before we look into the Great Plains low-level jet and ENSO relationship, we explored the simulation of the seasonality, climatological structure, and variability of Great Plains low-level jet in the FLORE model and its relation with U.S. rainfall. And FLORE has a very good simulation. So this motivates us to use FLORE to test this seasonality in the relationship using this long control run. So this slide is very similar to what you saw from observations, but from the FLORE controlled run data. The left side is the correlations of meridional wind at 925 hectopascal with Great Plains low-level jet index and with SST, and for the spring season, and the right side is for the summer season. Here you notice that the model does a good job during the spring season, where a stronger jet, that is a stronger southerlies, are associated with the La Nina phase. However, during summer, the stronger jet is also associated with La Nina phase. This is in contrast to observations where we noticed that the stronger jet was actually associated with an El Nino phase. So this suggests that the long control simulation seems to fail to simulate this seasonality in the relationship. So this might suggest that this relationship may be spurious and it could be just occurring by random chance. However, when we looked at another version of FLORE, which is the flux-adjusted version of FLORE, which has climatological SSTs and surface wind stress are closer to the observed estimates. And as you notice here that this model successfully simulates a seasonal change in the teleconnection, where in the spring season, the stronger jet is associated with La Nina. In summer, the stronger jet is associated with an El Nino. And this is consistent with observations. So there are two versions of model, where one model fails to simulate, whereas there is another version of the FLORE model which successfully simulates. So we wanted to understand why FLORE fails to simulate the seasonal change in this relationship. This question is important because this helps us to understand what does the coupled climate models need to get it right in order to get the seasonal change in the teleconnection between ENSO and Great Plains low-level jet, which will also help in the prediction of the Great Plains low-level jet. So in order to understand the reason for the discrepancy between FLORE and the flux-adjusted version of FLORE, we compared the mean state and variability of the Great Plains low-level jet itself between these two versions, and they seem to be comparable. And the second aspect we looked at was how are the tropical Atlantic conditions related to the Great Plains low-level jet comparable in these two versions, and they are also very similar. So the third aspect which is involved in this seasonal teleconnection is ENSO itself. So analysis of ENSO in these two versions of FLORE revealed that the ENSO amplitude and phase locking is different between the FLORE control run and the flux-adjusted version of FLORE. So here is the monthly standard deviation of NEO 3.4 index. And the black curve is for observations, red is for FLORE, and the green is for the flux-adjusted version of FLORE. As you can see that FLORE has very strong amplitude of ENSO and compared to observations, and also it peaks during the summer season and compared to the observations where it's seasonally phase locked at the end of the calendar year. But the floor flux-adjusted run tends to improve in the amplitude of ENSO, and more so it shows better simulation of the seasonal cycle of ENSO, where it peaks in end of calendar year consistent with observations. So we explore the hypothesis that coupled climate models which has better simulation of phase locking and strength of ENSO is important in order to simulate the seasonal change in the Tele connection between ENSO and the Great Plains low-level jet. So in order to test this hypothesis, we performed a model experiment. So as I mentioned in the previous slide, the flux-adjusted version of floor has better ENSO and thus leads to better relationship between ENSO and Great Plains low-level jet. So we use the ENSO from the floor flux-adjusted run and use that in the floor control run. So in the tropical Pacific, we restore the SST anomalies to the floor flux-adjusted anomalies. And everywhere else, in all the other ocean basins, it looks exactly similar like the floor control run, except that in the tropical Pacific, the ENSO looks like the ENSO from the floor flux-adjusted run. And this is run for 100 years, and here the restoring time scale is for 5 days. And as you can see that we overlay the regressions of NEO 3.4 index here, and this shows that the restoring region pretty much captures the ENSO variability region. So this is the results from the experimental run, and as you notice that it does a good job in spring, which was the case both in floor and floor FA. But in summer, you can see that this experimental run where in floor we put floor FA ENSO tend to simulate the seasonal change in Tele connection, where it's associated with La Nina in spring and El Nino-like SSTs in summer. However, you notice that these SST, the correlation values are much weaker compared to either the floor FA run or the observations. So even after, by restoring better ENSO seems to improve this Tele connection, but still it is not as strong as in observation. So this suggests that there should be some other factors other than ENSO which may be affecting the ENSO Great Plains low-level jet seasonal Tele connection. So we try to understand what are the other factors which may be interfering in this relationship. There are studies which suggest the role of North Pacific SSTs. So these studies state that the stronger Great Plains low-level jet happens when there is a warm phase of PDO. So in order to understand the role of North Pacific SSTs, here we show the composites of SST for the case of a stronger Great Plains low-level jet. That is, whenever a Great Plains low-level jet index is greater than 1 standard deviation. So the composites of SST on the left side is for spring season and the right side is for the summer season. And to summarize the tropical Pacific results, the top panel is for observations where we notice that the stronger jet is associated with La Nina in spring and El Nino in summer. That is, it shows a seasonal change in the Tele connection. Floor failed to simulate the seasonal change because in both the seasons it shows a negative correlation that it's associated with a La Nina. And floor flux-adjusted run was successful. The main motivation to show this slide was to concentrate on the North Pacific SSTs. From the observations, you notice that the stronger Great Plains low-level jet is associated with the negative SSTs in the central North Pacific, which is the typical signature of warm phase of PDO. Whereas in case of both the versions of GFTL model, it is associated with the cold phase of PDO. So we hypothesized that probably the negative SSTs of the cold phase of PDO, which extends from the west coast of North America over to the tropical Pacific, counteracts the positive SSTs and thus leads to a weaker relationship. So this is just a preliminary hypothesis which needs further investigation. So in order to just hint towards the plausibility of this hypothesis, we performed an flux-adjusted version of floor using flux-adjusted version of floor. We performed an experiment where we mask the ENSO variability. In the sense, in the tropical Pacific, we restore the SSTs to climatology, and in the sense that there is no ENSO anymore. And if you concentrate on the last right panel here, you notice that the stronger Great Plains low-level jet is associated with cold phase of PDO. So this suggests that independent of ENSO, the cold phase of PDO in GFTL models is associated with the Great Plains low-level jet, and it has a significant influence over this jet. The third objective of this talk is to understand the mechanism for seasonality in the ENSO Great Plains low-level jet relationship. There are studies such as Munoz and Enfield who suggest that the strength of the Great Plains low-level jet is related to the Caribbean low-level jet, through which it draws the moisture from the tropical Atlantic over to the United States. And there's another group of studies which suggest that ENSO has a lagged relationship with atmospheric conditions over the tropical Atlantic via the Walker and Hadley circulation. So in these lines, we propose a mechanistic hypothesis during spring as of how a La Nina is related to a stronger Great Plains low-level jet. The top panel is the correlation between the winter SST and the winter Nino 3.4 index. The last three panels are the correlation between spring SST, spring sea level pressure, and spring zonal winds at 925 hectopascal with the preceding winter Nino 3.4 index. And as you can notice here that the preceding winter La Nina conditions tend to persist into the succeeding spring season. And this preceding winter La Nina is also associated with significant atmospheric conditions over the Intra-Americas seas with a high sea level pressure anomalies which were induced by the Walker and Hadley circulations associated with ENSO, and which further leads to stronger easterlies, that is a stronger Caribbean low-level jet. And the Caribbean low-level jet is significantly correlated with a stronger Great Plains low-level jet with a correlation of 0.43. So this shows that the La Nina may be leading to a stronger Great Plains low-level jet via affecting the atmospheric conditions over the tropical Atlantic. Next, we propose a mechanism for the observed summer Tele connection. And this is the correlations between the summer sea level pressure anomalies and the Great Plains low-level jet index. And the bottom panel is the correlations with zonal wind at 925 hectopascal. And this map shows that it has a low sea level pressure anomalies in the tropical Pacific, which is a typical signature of El Nino, and high sea level pressure anomalies over the Intra-Americas seas. These high sea level pressure anomalies persisted from the spring season and were intensified by the atmosphere-ocean feedback during the summer season. So these opposite sea level pressure anomalies tend to introduce an SLP gradient between the tropical Atlantic and Pacific, which strengthens the easterlies over the Caribbean region, that is the Caribbean low-level jet. And this Caribbean low-level jet is also significantly correlated with Great Plains low-level jet with a correlation of 0.47. Thus, the El Nino is in the summer is also affecting the stronger Great Plains low-level jet via the tropical Atlantic. We have also explored this mechanistic hypothesis using the flow flux adjusted run, and we have also performed and explored this hypothesis in one of the experiments I mentioned earlier, where we masked the ENSO variability to check the relative roles of the tropical Pacific on the Great Plains low-level jet variability. And all these details can be found in this paper. Due to the interest of time, I'm not able to cover all those results. Finally, to conclude, observations suggest that there is a seasonal change in the teleconnection between ENSO and Great Plains low-level jet. During spring, it is negatively correlated, wherein La Nina leads to a stronger jet, whereas in summer, El Nino leads to a stronger jet. And using the two versions of GFTL model, we showed that it's important for the coupled climate models to have a better phase blocking and variability of ENSO to capture the ENSO Tele connection. And tropical Pacific is part of the story, and the other part of the story is explained by the North Pacific SSTs. And we also propose a mechanistic hypothesis that the tropical Pacific SSTs convey their influence on the Great Plains low-level jet via the tropical Atlantic. Thank you.
Thank you very much, Lakshmi. Eric, any thoughts or questions?
No, I think we can hear the questions from the audience.
Great, thank you. Is there anyone in the webcast who has any questions via chat, or raise your hand and we can take you off? Okay, looks like Ernesto has a question. Jill, could you unmute him, please? Great, Ernesto?
Hello?
Hi, go ahead.
Hi. Great talk, Krishnamurti. I really enjoyed your talk and the project that it describes. And I'm typing the question and also going to ask you, basically, aside from ENSO relationship, have you explored the Pacific North American pattern relationship with the Great Plains low-level jet from your simulations?
Yes. First, thanks for the compliment, and it's a good question. Actually, due to the interest of time, I couldn't cover that part of it, but this is explained in detail in my paper. So while we were looking at where I mentioned that we also tried to explore this mechanistic hypothesis in the model where there is no ENSO. So that the motivation for that was to understand what is the relative roles of the tropical Pacific versus North Pacific on the Great Plains low-level jet variability. So when we were looking at that run, we realized that during spring, there is an equal contribution from the North Pacific and tropical Pacific. So the way the North Pacific SSTs affect is through the PNA pattern. Whereas in summer, the major contribution is from the tropical Pacific. So yes, there is an impact of the PNA pattern on the Great Plains low-level jet.
Okay, got it. Thank you very much.
Thanks, Vasu. Do you have a question?
Yes, Lakshmi, this is Vasu from Florida State University. Excellent talk. I was wondering what happens in years when you have non-canonical evolution of SST in the tropical Atlantic. Usually when you have ENSO developing in the Eastern Pacific, you have warm SST anomalies developing in the spring over Northern Atlantic. And so you can talk of this gradient between the two ocean basins. But in years when you have this non-canonical SST evolution, which happens quite often, what is the explanation for the low-level jet modulation then?
So my understanding is when you mean by non-canonical, are you referring to where there is the opposite sign of anomalies in the east, something like a Central Pacific warming kind of thing?
When the SST anomalies in the Atlantic seem to be behaving independently of ENSO.
So I think, like I mentioned earlier, that there are years where there is a Great Plains low-level jet when there is no ENSO also. So it could be either there might be two things which could be driving. Either it could be that it is a seasonal manifestation of the synoptic scale low-level jet, or it could be that just the local condition in the tropical Atlantic could affect it, because we know there is an atmosphere-ocean feedback mechanism which occurs in the Intra-Americas seas. So when there is a cold SSTs, and there could be a west kind of feedback where it induces high sea level pressure, which in turn strengthens the low-level jet.
Let me see if I can rephrase the question. Have you seen in your 500 years or 600 years of the model simulation, in the flux-corrected model simulation, where the low-level jet seems to show the absence of seasonality in its relationship with ENSO?
Yes, there are years both in observations and the long control simulation.
Okay, and so have you been able to isolate the reason for the non-seasonality in such, have you been able to explain the reason for that behavior?
Actually, I haven't really investigated in detail, but from this analysis, my speculation is that, so not all years where there is ENSO makes a transition from La Nina to El Nino, right? So there may be years where it tends to persist. So, for example, let's take a scenario, for example, there was no seasonal change, for example, when there is a La Nina in spring and also a La Nina in summer, right? So that means there is no sea level pressure gradient. I guess that's what you're asking, right?
Right.
Yeah. So when there is no sea level pressure gradient, the atmospheric conditions which were induced from the previous spring, as I mentioned while I was explaining the mechanism, they tend to persist in summer in the tropical Atlantic. So now the tropical Pacific does not affect or has any significant influence on the low-level jet. It's the local conditions which persisted from this previous spring will affect the low-level jet. If at all, the La Nina may try to counteract that, because there is high pressure in both the basins, so probably the Caribbean low-level jet is not as strong. So when there is an El Nino, it tends to increase the variability of Caribbean low-level jet and thus the Great Plains low-level jet. Does it answer your question?
Yes, it does. Thanks.
Great. Thanks, Vasu. We have two more questions, if you don't mind answering them, and then we'll wrap up for the day. Great. One question is from Chen Zai. He asked, do other studies show that the Great Plains low-level jet during summer is controlled by the tropical North Atlantic sea surface temperature? Can you make a comment on this?
Yes, so I think the part of it which I also mentioned in my summer mechanism is the strengthening of the high sea level pressure and the strengthening of the Caribbean low level jet, even independent of El Nino, occurs through the effect of the tropical North Atlantic SSTs, that is the cold SSTs which are occurring. So they does contribute to it.
Great. And then the last question comes from Paula. Does this link change under CPW manifestations of INSO?
I haven't looked at it myself, but there are studies which show that there is a slight southward shift of the Great Plains low-level jet. My study mainly looks at when the Great Plains low-level jet is in place strengthening. But there are studies which have done like independent UF analysis on Great Plains low-level jet. I mean, they look at the meridional winds at 925 hectopascal. They do an UF analysis where they see that the first mode is related to the canonical INSO, and the second mode is actually related to the Central Pacific warming, but it's not the in-place strengthening of the winds, but there is a slight southward shift.
Okay. Thank you very much for your presentation today, and thanks to all the speakers. This is going to wrap up our day one of the virtual workshop. Hopefully you all join us back here tomorrow, starting at 1 p.m. Eastern Daylight Time, same place, same format. We have 2 sessions tomorrow. Session 3 is the weather and climate extremes in the Americas, and then we'll have another break for a different set of posters, and then we'll have the afternoon session on initiatives to improve observational coverage of the ocean, land, and atmosphere. Thank you all for tuning in, and we look forward to your participation tomorrow. Have a good afternoon.